Okay, another example. A girl of mass 50 kilograms stands on the rim of a merry-go-round. Radius is 2 meters. Rotational inertia of the merry-go-round is 800. Okay. By the way, the unit of the rotational inertia is kilogram multiplied by meter squared, because that's m. It's always in the form of mr squared. Okay. Initially, it's not moving, and then the girl throws a rock of mass m equals to 0.5 kilogram horizontally in the direction that is tangent to the outer ridge of the merry-go-round. The speed of the rock relative to the ground is 4 meters per second. What is the angular speed of the merry-go-round, and what is the linear speed of the girl after she throws this rock? Okay, it's something like this. We have a merry-go-round. Initially, it's rest. A girl is standing at the edge, and he has some rock, okay, on hand. Initially, it's stationary here, and then she will throw the rock into some direction. Okay, suppose it's to this direction. Okay, tangent to the merry-go-round. So you can see the reaction will push the girl together with the merry-go-round to rotate to that direction, right? Okay. So that omega is the quantity we want to find. We also want to find the linear speed of the girl to get with the rotation. Of course, after we find omega, we can find v for the girl, right? Okay. So what we know is that the speed of the rock is 4 meters per second. Okay, and the mass, let's call it m, small m, is what's that? 0.5, and the capital M is the mass of the girl is 50 kilograms, right? And the rotational inertia for the merry-go-round I equals to 800. Okay? Okay, so that's the known quantity we put here. Now, what we are going to calculate, you can think about this there is no external torque. The motion, okay, is introduced by some action and reaction, some internal force. Okay, initially it stays there. After she throws this rock, and then the reaction will make it rotate, just like the coupling. There is no external torque. So the angular momentum should be conserved. Initial angular momentum should be the same as the final angular momentum. And what is the initial angular momentum here? For the system, what is the initial angular momentum?
It's not moving.
It's 0?
0, okay? Angular momentum is some quantity to characterize the rotation. So that if nothing is in rotation, the angular momentum is 0. And final angular momentum should have 3 terms, right? The angular momentum from the rock, the angular momentum of the girl, the angular momentum of the merry-go-round. Okay, let's call them L1, L2, and L3. L1 is for the rock, L2 is for the girl, and L3 is for merry-go-round. Okay, now we need to determine the positive and negative side for the 3 terms. How about L1?
Negative.
Negative clockwise. Okay. How about L2?
Positive.
Positive. How about L3?
Positive.
Positive. Okay. So that's the equation you are going to use. And now we're going to use some kind of definition, to calculate each term. For L1, how would like you to calculate the angular momentum? You know the mass, you know the velocity. By the way, do we know the radius for
Yes.
the merry-go-round? Okay, r equals to 2 meters. So the best equation for L1 should be 0 equals to negative. L1 should be I think the best one is mvr perpendicular. Okay. M is the mass given, V0 is given, and R perpendicular in this case should be the same as R, the radius, right? Okay? Any question here? Because it's in the tangential direction, so it's perpendicular to R. In this case, R is the same as R perpendicular. Now, L2, okay, so again we can use M, so here is capital M, and V, that's a velocity we want to find for the girl, multiplied by R perpendicular. So it will capital M V R. Again, for the girl, R perpendicular is R. Okay. Please note that I always write down R perpendicular first, and then write it as R. Even in this case, R perpendicular is exactly the same as R. Try to keep this when you do that, because in some other problem, R perpendicular may not be the same as R. So it kind of give you some step for you to think about. Okay, you need to determine if R perpendicular equals to R, or maybe R multiplied by sine theta, or R multiplied by cosine theta, something like that. Okay. So here, and then our L3. L3 it's better to use I omega, right? Because I is given, it's an extended body. So you can use I omega. Omega is the unknown quantity we want to find. So if you put them in the equation, you get 0 equals to negative mv naught r plus capital M V R plus I omega. Okay? So there is one issue here, is that we have two unknown quantities, V and omega. So you will not be able to solve it with one equation. How can we do that? Please note that there is some relationship between V and omega. What's that? V equals to omega r, right? The tangential velocity equals to the angular velocity multiplied by the radius. So if you put it here, then you get one equation with one unknown quantity, omega r squared. Then you have one more r, right? Plus I omega. So that's one equation for one unknown quantity, omega. So you can solve it for omega. Once you have the omega, put it in here, you get V. Any question? Okay, so that's the problem.